Hello and welcome to today's video. Today we're going to be talking about optimization of composites. We're going to be looking at optimization of composites within a software package called Design Studio. So we'll be looking at a simple 3-point bend test. We'll be looking at assessing the stiffness of a structure as if it were made out of another material, let's say steel, and then we'll look at that as if it were laid up arbitrarily in a composite structure using pre-preg, so laid up in some random order. We'll measure the stiffness of that and compare that to the steel structure. We'll then look at optimizing the structure, so we'll look at optimizing the layout, the number of plies, the orientation of those plies, and show that hopefully that we get a much more efficient structure by doing that. We'll then have a look at introducing some manufacturing constraints, so understanding discrete variables. So we have a whole number of plies, and we'll compare that to the theoretical optimized stiffness, and then back to the arbitrarily laid up stiffness and the baseline structure stiffness. We're going to be using Design Studio to do this. It doesn't actually matter what software we're using or what version of the software we're going to be using. So I'll be doing it within this package. Don't worry too much if you can't follow it, if you don't understand exactly what buttons I'm pushing and so on. That's not the purpose of this video. I'll be talking through the process and we'll be understanding the implications of setting up variables, objectives, constraints, that sort of thing. And we'll be talking about making those variables discrete and so on. What I want you to get out of today's video is to show you how powerful these sorts of techniques are when we're dealing with these orthotropic materials. They give us a great deal of problems compared to isotropic materials if we don't know what we're doing. But actually, if we do know what we're doing, if we're using software such as the software we're using today, they give us a great deal of opportunity in terms of optimizing the stiffness in the orientation that we want it. So we end up with much lighter, stiffer materials. So our stiffness to weight ratio is much better. So sit back, watch the video, understand what we're doing. I'll talk us through the process. In terms of understanding exactly what buttons to press, I will help you guys when we're doing that in class, and I'll set aside some time so that I can help you go through this process in class. But like I say, the purpose of today's video is really just to describe what we're doing, why we're doing it, and to demonstrate how powerful optimization using finite element analysis optimization is in terms of us developing much more efficient structures. So here's our structure. We've got a simply supported structure. It's 150 mil long by 25 mil wide. It's a piece of steel plate. It's 3 millimeters thick. We've got a force of 500 newtons as a UDL, so evenly spread out all the way across the plate. It's set up so that it can rotate freely at both ends. And it can translate at one end. So if I show you the load case, there's the load case. If we look at this end, we can see that that can move in degrees of freedom 1, 2, 3, 4, and 6. So degree of freedom 5 is missing, so it can rotate around that axis. And at this end here, if I change the display, if I go into display there, we can see at this end here, we've got that degree of freedom missing, but it can also translate in 1. 1 is also missing, so it can translate in the x-axis. Okay, if I then show you the results of what's going on with this baseline steel part, if I go to clear all and animate that, deform mesh, color mesh, there's our displacement. We can see our baseline stiffness, our baseline structure. So this is our steel structure. It's displacing by 1.9 times 10⁻³ meters, so 1.9 millimeters. in the center, which is exactly what we'd expect, and we can see that clearly it is allowed to rotate at either end. So it's rotating about this axis here. It's also rotating about this axis here, and because we're allowing it to translate at one end, there's no restriction there. It's displacing by 1.9 millimeters. So that's going to be our target stiffness. Okay, we've got this steel structure. Like I say, it's 3 mil thick. That's the loading on it gives us 1.9 millimeters of deflection in the center, so we can calculate the stiffness. What we're going to do in today's class, we're going to set up a composite structure arbitrarily, with an arbitrary layup to understand the stiffness to weight ratio of that composite structure, and then we're going to use optimization techniques to determine how we should lay this up to give us the most efficient structure in terms of its stiffness to weight ratio, and then we'll consider the manufacturing constraints as well. So there's our target stiffness. Going to need to know the weight of the structure so that we can work out the stiffness to weight ratio, and then we can compare that to our composite structure. So remember, this is our steel structure. We can calculate the stiffness. I'll do that in a minute. In order to calculate the weight, the first thing we're going to need to do is to calculate the mass. So I'll just go into analysis, elements, select all, calculate mass, and we can see our mass summary 0.086625 kilograms. So what's that? 1, 2, 3, 86.6 grams, 87 grams. Okay, so let's have a think about what our structure is then. So we've got this beam. It is simply supported. So we've got supports at this end, got supports at this end. One end we're allowing it to translate. We've got a uniformly distributed load on top of that. 500 newtons. So our deformed shape looks something like this. Okay. So it's rotating around the three ends, around this end here, around this axis. It's rotating and translating around this end. We've got our uniformly distributed load on there, 500 newtons, and we've got a displacement of 1.9 millimeters in the middle. Okay, so let's calculate the stiffness to weight ratio for this structure. Okay, the baseline structure. So for the steel structure, what have we got? Our stiffness, F equals Kx, Hooke's law. So K equals F over X. Our force is 500 newtons. And our displacement is 1.9 millimeters. So divided by 1.9 gives us 263 newtons per millimeter. Okay, that's the stiffness. Okay, now the mass we've just seen was 87 grams. So therefore the stiffness to weight ratio for our baseline steel structure equals 263 newtons per millimeter. That's the stiffness, and the weight is the mass times by gravity, so that's going to be 0.087 kilograms times by 9.81, so we'll times that by gravity. So mass times by gravity, so that's going to be our weight. Gives us 308 newtons squared per millimeters. Okay, odd units. Don't worry too much about the units, it's this number that's important to us. We're going to be comparing this steel baseline. So let's call this baseline. Our steel baseline, our stiffness to weight ratio, 308 newtons per millimeter. Let's compare that to our composite structure. Like I say, first thing we're going to do is arbitrarily lay that up, and then we'll compare that to the optimized structure, and then the optimized structure considering manufacturability. So there's our stiffness to weight ratio of our baseline steel part. Let's now set up an arbitrarily laid up composite structure. We're going to assume that this is made up of a unidirectional composite. So what do I mean by that? If we consider our structure, something like this. I'll try and draw it in 3 dimensions. There's our structure. We've got fibres running lengthways down our structure. So let's say we've got some fibres on here, and it's unidirectional. So that means we've got long continuous fibres, and they're all running in the same orientation. So our fibres would run lengthways down our structure, looking something like this. Okay, we've got a unidirectional composite. Okay, what does that mean? That means that the stiffness in this orientation, we'll call E1, is going to be quite high. It's going to be driven by the stiffness of the carbon fibres. And the stiffness in this direction, which we'll call E2, is going to be much lower, the lateral stiffness, and that's going to be driven by the stiffness of the epoxy. We've got carbon fibre reinforced plastics, and the plastic, the epoxy, the stiffness is going to drive E2. So let's now set up that material within Design Studio. We're going to be using this unidirectional material, and I'll upload this PDF file describing what's going on. And in this PDF file, you can see there are material properties. So when we're dealing with this orthotropic material, we've got E1, 132 gigapascals. So that's driven by these carbon fibres. We've got the Young's modulus in the lateral direction, E2, 10.8 gigapascals. That's going to be the stiffness driven by the epoxy. And then we've got Poisson's ratio, in-plane shear modulus, transverse shear modulus, and so on. And then allowable stress in tension and compression in X, tension and compression in Y, and allowable shear stress if we are looking at failure of our composite materials. So let's set that up within Design Studio. So if we move to Design Studio, and what we're going to do now, if we go to Analysis and then Materials, we create a new material. This is going to be an orthotropic material, and we'll call this our carbon fibre reinforced plastic, CFRP. And you can see there, E1 is 132. Now remember, we're working in SI units, 132 gigapascals, so that's times 10 to the 9. You can just write 132 E9, 10.8, 10.8 E9 for E2, 0.24 for Poisson's ratio. So I'm just copying these numbers from that PDF. 5.65 times 10 to the 9 for G12. G1Z, G2Z is exactly the same. Rho is 1,540 kilograms per meter cubed. We've then got some thermal expansion coefficient numbers. We'll ignore those, so we can jump straight down to XT, the allowable stress in tension. That's 1513 megapascals, so that's E to the 6. And then allowable stress in tension, 43.4 times 10 to the 6, 43.4 megapascals. Same for Y tension, Y compression, shear. Oh, sorry, I've got the XC, allowable stress in tension in the X direction, is 1,000 megapascals. So that's 1,000 E6. Okay. Just check those. Yeah, that looks right. Click on next and then finish. Okay, so we've got two different materials now. Okay, we've got mat 1, which was our steel. If we click on that and click on edit, we can see it's an isotropic material, Young's modulus, Poisson's ratio, and so on for steel. We've got our carbon fiber now. If I click on edit, and there's our unidirectional carbon fiber material properties that we've just put in there. So we've now defined two materials in this model. We've got these elements here, which are currently pointing to this 3mm steel, and that isotropic material. That's given us our stiffness to weight ratio of 308 newtons squared per millimeter. We've also got an orthotropic material now defined, this unidirectional carbon fiber, and where E1 and E2 are clearly different. So when we're dealing with an isotropic material, the orientation of these elements doesn't matter, because the stiffness of the material in all directions is exactly the same. However, as soon as we define an orthotropic material, we have different stiffnesses in different directions. So therefore, the orientation of the elements is clearly important, and we need to understand the orientation of those elements to make sure that we've got E1 in the direction we want it, and E2 in the direction that we want it. So E1, remember, is driven by the stiffness of the fibers. We're going to assume that E1 is running along the length of this structure, and E2 is going to be running laterally along this structure. So we want to orientate this now such that the orientation of the elements means that E1 is running in this direction along the length of the structure. Now, to see that, if we go to elements, analysis, elements, select all, generate theta vectors, there we go. We can see those vectors. We can think of those as our fibers, and our fibers clearly are now running down the length of the structure, which is exactly what we want. Now, we can change those if we wanted to change the orientation of those vectors. We just go to analysis, elements, modify, change 2D theta. Let's use the vector by 2 grids. So let's choose the lateral direction. Next, finish. If I now go to generate theta vectors, where I can see that the fibers are running widthwise. So if I were to create the model like this, E1 would be lateral along the width of the structure, but we don't actually want that. So if we go back to the original situation, so we'll go elements, modify, change 2D theta, click on next, by 2 grids. This time we'll choose 2 grids running down the length of the structure. So let's choose this grid here and this grid here. So that defines that vector there. Click on next and finish. And now if I go to generate theta vectors again, there again, I can see that the fibers are now running down the length of the structure. So E1 is running in this orientation. So we now understand the orientation of the elements. However, they're still pointing to this steel material. They're still made from this 3mm thick steel material. And we can check that if we go to analysis, group properties, and they're pointing to this P shell. If we click on edit, we can see that's made up of this 3mm material, and it's pointing to mat 1. We know if we look at our materials and we go into mat 1, that's this isotropic material. There's our material properties for steel. So it's made from 3mm steel, and we can see that if we go to our group properties. It's currently red. These elements are currently red. Okay, so what we need to do is to define this composite layup, which we're going to point these elements to, which link to that unidirectional composite material that we have just defined. So let's now define how we're going to lay out this structure. At the moment, there's one physical property, P shell. That is saying that these elements are all made from steel and they're 3 millimeters thick. Okay, we're going to define something called a P-comp. That will define how our composite material is laid up. Initially, we're going to lay that up arbitrarily. We are going to assume that each layer of prepreg is 0.2 millimeters, and we're going to assume that there's 5 plies at minus 90, i.e. laterally along the structure, 5 plies at minus 45, 5 plies at 0, 5 plies at 45, and then 5 plies at 90. So there's going to be 5 layers. Each of those layers is going to contain 5 plies. Each ply is 0.2 millimeters. So each layer is going to be 1 millimeters thick. Okay, so if we have a look at the PDF, so layer 1 is going to be 1 millimeters thick. It's orientated at 90 degrees, i.e. it's got 5 plies. Notice the subtle difference there between a ply and a layer. Okay, so we've got one layer which has got 5 plies in it. We know that because each ply is going to be 0.2 millimeters. So the fact that this this layer is 1 millimeters means it must have 5 plies in it, and that's going to be orientated at minus 90 degrees. Remember, 0 degrees we've just defined as the orientation of the elements running lengthways down our structure. Okay, so layer 1 made up of this unidirectional material. It's 1 mil thick, therefore it's 5 plies, and all of those plies are orientated at minus 90 degrees. Layer 2 made up of this unidirectional material, 1 mil thick at minus 45. Layer 3, 1 mil thick, 0 degrees. Layer 4, 1 mil thick, 45 degrees. Layer 5, 1 mil thick, 90 degrees. Okay, so there's 5 plies at minus 90, there's 5 plies at minus 45, 5 plies at 0, 5 plies at 45, and 5 plies at 90 degrees. So there's 5, 10, 15, 20, 25 plies laid up arbitrarily. This thing is going to be 5 millimeters thick. There's 25 plies. Each one is 0.2 millimeters. So that gives us a total thickness of 5 mil. So remember, our baseline steel structure was 3 millimeters thick, made up of steel. This arbitrarily laid up structure with this unidirectional composite material is going to be 5 mil thick, 5 plies at minus 90, 5 at minus 45, 5 at 0, 5 at 45, 5 at 90. Okay, let's now define that P-comp so that we can point those elements to that arbitrarily laid up composite structure. So let's go into analysis, group properties, and we're going to define a new group property. Okay, let's our steel material properties or our steel physical property is made up of these red elements. Let's define our arbitrarily laid up composite structure as green, and let's just call this UD. But instead of the type P shell, we want a composite material, so we're going to point that to P comp. Okay, if we click on next, it's then asking us what material is it made from, what's the thickness of each layer, what is the angle of that layer. Okay, so and we can then add subsequent layers. So the first layer, we're going to point to this carbon fiber, this UD. We assume it's 1 mil thick, so 1E minus 3. Remember, we're working in SI units, and its orientation is going to be minus 90. Okay, we click on plus to add another layer, which is also carbon fiber, so it copies across everything that we've put in there. So carbon fiber, 1 mil thick at minus 45 degrees. Add another layer, carbon fiber, 1 mil thick at 0 degrees. Add another layer, carbon fiber, 1 mil thick at 45 degrees. Add another layer, carbon fiber, 1 mil thick at 90 degrees. Okay, so we've got 5 layers there. 1, 2, 3, 4, 5. Each one is 1 mil thick. So therefore it must have 5 plies. So we've defined our layout exactly as we've just been describing. Okay, and it says down the bottom there actually total thickness 5 mil, which is what we would expect. So if we click on finish, we've now got our red physical property, which these elements are still pointing to. We can see that. If we click on that red physical property, all these elements are highlighted. This green one, which we've just defined, this P-comp, that's grayed out actually because there's no elements in that physical property. So what we need to do now is to point these elements to this new physical property, which we have just created, this P-comp. Okay, so we can go analysis, elements, select all, modify, change group, change element group, click on next, pick on P-comp, which we've just defined, and then click on finish. And we can see all of those elements now have just suddenly turned green because they're no longer pointing to that physical property, which was pointing to those steel properties, material properties. If we go to group properties now, we can see green is highlighted. If we click on that, we can see those green elements. They're made up of that physical property which we've just defined. And now the red one actually is grayed out because there's no elements in that because we've just moved them. So we've assessed this structure as a 3mm steel structure. We've now changed it to a unidirectional composite structure, which is arbitrarily laid up with these 25 plies, 5 at -90, 5 at -45, and so on. Okay. So let's assess that arbitrarily laid up composite structure so that we can compare the stiffness to weight ratio of that with the stiffness to weight ratio of the steel structure. Okay, so now that we've defined that, we can just go to Genesis, single analysis, redefine that, rerun that, should I say. We go to import post, click on our structure, on our results file, click on close. We go to post, deform mesh, color mesh. There's our structure, and we can see the deformed shape. Okay, so that has now deformed by 5.8mm. Okay, so remember the steel structure deformed by 1.9mm. The carbon fiber, arbitrarily laid up carbon fiber structure has deformed by 5.8mm. Okay, now in order to work out the stiffness to weight ratio, we are also going to need to understand the mass of this structure so that we can work out the weight of this structure. So if we just go to analysis, elements, select all, and calculate mass, we can see down here now that that is 0.0288 kilograms. So what's that? 28.8 grams, 29 grams. Okay, so we can now work out the stiffness to weight ratio of this arbitrarily laid up composite structure. So what we can do now is compare the stiffness to weight ratio of this arbitrarily laid up composite structure with the stiffness to weight ratio of the baseline steel structure. Now, remember the baseline steel structure? Now, steel structure, baseline. What did we work out for that? That was, so the stiffness was 263 newtons per millimeter. The mass was 87 grams, and that gave us a stiffness to weight ratio of 308 newtons squared per millimeter. Like I say, don't worry too much about those strange units. The thing that's important is that number there, 308 newtons per millimeter. Let's now compare that to this arbitrarily laid up carbon fiber reinforced plastic structure. Okay, let's work it out in the same way. Okay, so
K equals F over X equals, what was our force? Our force is the same, so that's 500 newtons. Our displacement, however, this time is 5.8 millimeters. That's what we've just seen, 5.8 millimeters. So that gives me a stiffness to weight ratio of 86 newtons per millimeter. Okay, so stiffness to weight ratio. So we can see the stiffness of the steel structure is much higher than the stiffness of the carbon fiber structure. Okay. However, let's now consider mass. Now our mass was 29 grams. So our stiffness to weight ratio is 86 divided by 0.0229 grams times by 9.81, which is going to give us 297 newtons squared per millimeter. Okay. Compare that to the stiffness to weight ratio of the steel structure. It's basically the same, 300 newtons squared per millimeter. The number is basically the same, 297, 308. So in terms of stiffness to weight ratio, having an arbitrarily laid up composite structure offers us no benefit compared to steel in this scenario. Okay, so what we're going to do now is we're going to, instead of arbitrarily laying that up with 5 plies at -90, 5 plies at -45, 5 plies at 0, and so on, we're actually going to define variables, objectives, constraints within our structure to define how many plies we need in each layer to give us the same stiffness. This stiffness here was our steel structure. Okay, and hopefully by doing that we'll have a much lower mass, so therefore our stiffness to weight ratio will be better. Okay.
Now, we saw in the last video that when we optimize something, we need variables, objectives, and constraints. Okay, so our variables this time are going to be the thicknesses of each of those layers. At the moment, they're 1 mil thick, so they've got 5 plies in each orientation. Our objective is going to be to minimize mass. We want to make it as light as possible. And our constraint is the same displacement, 1.9 millimeters as the baseline still. So by doing that, we should increase the stiffness to weight ratio. So let's define those. So let's go to design, objective, new objective, and our objective mass, minimize mass, finish. That's it. We now have an objective. Next, we're going to define our constraint. So let's go to constraint, new constraint, a displacement constraint, and we're going to put a upper bound of 1.9 millimeters, 1.9 times 10 to the -3. So we've got an upper bound of 1.9 millimeters. Click on next, translation magnitude. Select all our grids, so we don't want any of them to displace by more than 1.9 millimeters. Clearly, it's going to be the grids in the middle which are going to displace most, but we're just simply going to select all and click on translation magnitude, click on next, or that load case. There's only one load case in this model, and then finish. Okay. Next, we are going to need to define the variables. Okay. Now, when we define the variables, we're going to have 5 variables. That is the thickness of each layer. Okay, so let's go out to our design variables. We'll click on new design variable. We need to be fairly methodical here, so we'll call this layer 1. Layer 1 thickness. It's going to be an independent design variable to start with. We'll just accept that default. Click on next. Okay, so the initial value is 1 mil, 1 times 10 minus 3. We've assumed 5 pliers. The lower bound, let's say, is 0.2 mil, so we have to have at least 1 ply in each orientation. So 0.2 times 10 to the minus 3, and the upper bound, let's set that at 3 millimeters, 3 times 10 to the minus 3. So what we're doing here, if we look at the PDF, which is this one here, there's our PDF. We've now defined our objective and our constraint. We're now defining our variables. There's our variables. Look, 5 variables. Initial value, they're all at 1 mil. So we've got 5 plies in each orientation. Lower bound, 0.2 mil. Upper bound, 3 mil. Okay. And there's our description of each variable. So we've got 5 variables. So let's finish defining those. Go back into Design Studio. So initial value 1 mil, lower bound 0.2 mil, upper bound 3 mil. Click on finish. That is layer 1 thickness. If we now click on that and click on copy and then paste, we're going to need 5 of those. 1, 2, 3, 4, 5. 5. Click on that to modify that. Let's just modify the name. Click on modify. So instead of that being called copy of layer 1, let's call that layer 2 thickness. Finish. Modify that one to layer 3 thickness. Modify that one to layer 4 thickness. And modify that variable to layer 5 thickness. Okay, now at the moment we've got 5 variables, but those 5 variables at the moment are not pointing to our physical property. So what we're going to need to do now, if we go to sizing, we're going to size that physical property. So we're going to go to sizing, we're going to click on our physical property, click on modify, and at the moment it says the material is made of carbon, so we've got 5 layers in each of these orientations. Layer 1 was at minus 90, layer 5 was at layer 2, sorry, was at minus 45, layer 3 was at 0, layer 4 was at 45, and layer 5 is at 90. Okay, so the angles are not going to change. The thicknesses at the moment, they're all 1 mil. So layer 1 we can see is 1 mil and it says not designed. Layer 2, 1 mil, not designed. Layer 3, 1 mil, not designed. They're all assuming that we've got 5 plies in each orientation. So layer 1, let's change the thickness to point to the variable layer 1 thickness. And now it is defined. We've got a lower bound of 0.2 and an upper bound of 3. That's what we've just defined in our variables. Layer 2, we're going to point to layer 2, the variable layer 2 thickness. Layer 3, we're going to point to the variable layer 3 thickness. Layer 4, we're going to point to the variable layer 4 thickness. Layer 5, we're going to point to the variable layer 5 thickness. Okay, and then we'll click on finish. So there you can understand why we're needing to be fairly methodical with our naming convention. That now should be ready to optimize. If we click on Genesis, and you can see now optimize is there. We're ready to optimize our structure. Prior to that, that would have been grayed out. But now we have defined the 3 things which are necessary for an optimization run, i.e. variables, objectives, constraints. We can optimize that structure. Remember, our variables are the thicknesses of each of those layers between 0.2, so that is 1 ply, and 3 mil. What's that? 15 plies in each orientation. So those are our variables. Our objective is to make it as light as possible, and our constraint is so that we have the same stiffness as the steel structure. So now if we just click on optimize, the Genesis or Design Studio should optimize our structure, taking those things into account. I just moved that. Oh, okay. What's happened there? We've reached the maximum number of cycles. It's possible, as I was talking about in the last video, that you set an impossible task. So by default, what Genesis has done, it sets the maximum design cycles to 10. And what it's saying there is the maximum cycles has been reached. So therefore it's stopped. So if we just go to Genesis and go to options, and we can change the design control, maximum number of cycles. Let's change that to, I don't know, 30, and click on apply. It now should optimize beyond those 10 cycles. It will optimize up to potentially 30 design cycles. So I'll just click on design, Genesis, optimize, and it's now running again. When it runs, it's generating this graph. So what's happening there? Okay, we can see that has now converged in 13 design cycles. We've got hard convergence there. Okay, so our objective on this top graph here, look, the y-axis is objective and the x-axis is the design cycle. Our objective was to minimize mass. Okay, now the objective initially, the design cycle 0, our baseline structure, if we click on that, if we hold our mouse over that, we can see that is 29 grams. That was our mass. Remember, our objective was to minimize mass. So our mass started off at 29 grams. And it's increased up here, up to, by design cycle 2, look, to 40 grams. And then it starts to come down again. Okay, as Design Studio is orientated or playing around with those pliers to minimize the objective. So there's our mass initially at 29 grams, goes up to 40 grams by design cycle 2, and then back down here by design cycle 13 is back at 30 grams down. Okay, and our bottom graph now, if we look at the y-axis, that's our max constraint violation in the y-axis, and the x-axis is the design cycle. So initially, it was violating the constraint. It was displacing by more than 1.9 millimeters. We saw earlier it was displacing by 5.8 millimeters. We're violating our constraint with our baseline structure, with our arbitrarily laid up composite structure. Okay, so initially it's throwing mass at the structure. You can see the objective is going up to get the constraint down. So by design cycle 2, we're no longer violating our constraint. We've gone down to 0, represented by these green dots here. We're no longer violating the constraint. And then after design cycle 2, we're getting mass out of the structure, which is what we want. We want to minimize mass. We're getting mass out of the structure, and you can see we're still not violating the constraint. So let's read in those results and let's see what's happened. So if we click on close, import post, I'm going to read everything in. I'm going to hold down shift, click on the last design cycle, click on import, and we'll have a look at those results. So if I go to post and go to deform mesh color mesh, there you can see I've got my baseline structure here for still under deform mesh for design cycle 0, and then I've got my optimization one, which has gone from design cycle 0, 1, 2, 3, all the way down to design cycle 13. Okay, now if I click on my results, my deformed shape should basically be the same for all those design cycles, I would think. So I can click on all of those, and that's showing the deformed shape of my structure. Initially, we're seeing 5.8 millimeters. If I click on the displacement for the baseline structure, it's 5.8 millimeters. If I click on the displacement for design cycle 0, 5.8 millimeters. So that's the initial design. That's design cycle 0, which was also the initial design. So therefore, we've got the same displacement, 5.8 millimeters. If I click on design cycle 1 displacement, that's gone up to it's gone down to 2.6 millimeters. But remember, our mass went up. We're throwing mass at our structure, so we are no longer violating our constraint. Okay. And then if we scroll down to design cycle 13, displacement 1.9 millimeters. Remember, that was our constraint. That's what we asked Design Studio to meet, 1.9 millimeters. So our stiffness for our optimized composite structure is now the same as our baseline steel. Remember, our baseline steel had 500 newtons on it and had a displacement of 1.9 mil. My optimized composite structure also has 500 newtons on it and also has a displacement of 1.9 millimeters. So therefore, the stiffness is going to be exactly the same. If I look at the layup, initially, all of my layers are 1 mil thick, and my angle -90, -45, 0, 45, and 90. Okay, by the time I get to design cycle 13, I scroll down to design cycle 13, my layer 1 thickness is now 0.000252 millimeters. Layer 2 is 0.00847 millimeters, and so on. Layer 3 is 3 mil, which is the maximum, which is what we do expect. Those are the elements with the orientation of the fibers at 0 degrees, i.e. running lengthways down the structure. Those are the ones which are going to contribute most to the stiffness, looking at the deformed shape of the structure. And then our angles didn't change. They're -90 still, -45, 0, 45, 90. So what is of interest to me is what has happened to the thicknesses of each of those layers to meet that stiffness of 1.9 or that displacement of 1.9 millimeters. If we then take the thicknesses of each of those layers and divide it by 0.2, because we know each ply is 0.2 millimeters, that will tell me how many plies we need in each orientation. So let's now do that. When we optimize anything in Design Studio, it creates something called a history file, and the history file just plots how the variables have changed over the design cycles, so that we can extract that information. So let's go to File, Import, Design History Results. It automatically filters for that history file. Click on Open. On Up, and then I'm going to go into Design History Plot. I'm going to go to a new Design History Plot. I'm going to add some information. I'm going to add some information about the variables, so click on that. From that file, they're the ones that I'm interested in, the design variable thicknesses. Click on Next, so I'm going to hold down Shift, click on those, click on Next, and there we can see how those design variables have changed. Okay, so hopefully you can see that, or if not, just work through that and you'll see that when you run that yourself. Initially, we've got 5 design variables. Design variable 1 is layer 1 thickness, and that's in red. Design variable 2 is in blue, that's layer 2 thickness, and so on. Okay, initially they're all 1 mil thick. We can see the green ones, so that's design variable 3, goes up to 3 mil thick. Design variables, this one here in brown, that's design variable 4. That would also be design variable 2. Overlaid over the top of that, you can just about see it. So that again, that starts off at 1 mil thick and goes down to this value here. It ends up at design cycle 13 at 0.847 millimeters thick. And then we've got these here. You can just about see we've got the cyan one and the red one. So those are the plies at -90 and at 90 degrees. They start off at 1 mil thick and they go down to a minimum, or down to this value here, 0.251 millimeters thick. Okay, so we can see how the thicknesses of each of the variables change over the optimization. Now, the history file is just a text file. and that will tell us how the design variables has changed over each design cycle. It will also tell us how the objective has changed and the constraint has changed over each design cycle. So let's now open that and examine that. Okay, so if I just minimize that screen, let's close that window. Let's have a look at that file. So in here, I'm running the job under downloads. There will be, oh, sorry, under here, there'll be a history file. If I'll just search for .his, and I just open that in a text editor. I just right click on that and go open with, okay, edit with Notepad, that'll do. We can see how the violation has changed, how the variables have all changed, and how the objective has changed. So initially, design cycle 0, the objective was 29 grams, remember? It violated but the constraint by 207 degrees, and each variable was 1 mil thick, look. If we now go down to the last design cycle, our objective is now 29.97697 times 10 to minus 2 kilograms. So what's that? 29.30 grams. However, importantly, it's no longer violating the constraint, and we can work out the thickness. We can see the thicknesses of each of the layers, and if we divide those thicknesses by the thickness of one ply, we can work out how many plies we need in each orientation to get the same stiffness as the steel structure. So let's now have a look at our PDF, which summarizes what we've seen so far. Okay, so our baseline steel structure here, look, material was steel, it was 3 mil thick, had a deflection of 1.9 millimeters, the mass was 97 grams. The load is 500 newtons, so that gave us our stiffness of 263 newtons per millimeter and our stiffness to weight ratio of 308 newtons per millimeter, newtons squared per millimeter. Our composite baseline was 5 mil, so we had 5 layers, each layer with 5 plies, so it was 25 plies thick, remember. Our deflection was 5.8 millimeters, our mass was 29 grams, our load was 500 newtons, which gave me a stiffness of 86 newtons per millimeter squared, and our stiffness to weight ratio was basically the same. There was no advantage with our arbitrarily laid up composite structure. When we look at our optimized composite structure, however, look at what's changed. Okay, so our thickness has gone up to 5.2 mil. If we consider the thicknesses of each of those layers. However, the deflection is down to 1.9 millimeters because that was our constraint, and the mass is 30 grams. The load is still 500 newtons, so our stiffness is going to be exactly the same. Okay, same load, same deflection. Okay, 263 newtons per millimeter. But interestingly and importantly, when we look at our stiffness to weight ratio, we've gone from 308 newtons squared per millimeter to 894 newtons squared per millimeter. So it's nearly, in terms of stiffness to weight ratio, it's nearly 3 times better as our original part. However, if we were to look at the history file, and here I've just taken a screenshot of the design variables for the last cycle, you can see the thicknesses of each of those variables. Okay, so layer 1 was 2.62257 times 10 to the minus 4 millimeters. If we divide that by 0.2 millimeters, that's going to give me 1.3 plies. So the optimization is telling me we want 1.3 plies at minus 90, 4.25 plies at minus 45, 15 plies at 0, 4.15 plies at 45, 1.35 plies at 90. Okay, now clearly that's not taking manufacturing into account. We can't have 1.3 plies at minus 90. We could have 1 ply or 2 plies, but we can't have 1.3 plies at minus 90. So what we've done there is we have looked at the optimum solution without taking manufacturing into account. We've got real numbers for our variables. They were between 0.2 millimeters and 3 millimeters. What we now need to do is consider them as discrete variables, i.e. 0.2 millimeters, 0.4 millimeters, 0.6 millimeters, and so on. We can choose one of those values, but what we can't do is choose other values between that maximum and that minimum. So our minimum is 0.2, our maximum is 3. Okay, so what we're going to have to do now is we will define those variables as discrete variables and look at, when we take manufacturing into account, what our layup actually is. We should see that our stiffness to weight ratio will not be quite as good, but we'll actually be able to manufacture the thing. Okay, so in the next video, and I will need to do a second video to show this. In the next video, what I'll do, I'll take those design variables and I'll change them to discrete design variables, and we will re-optimize it, and we will look at the comparison. Okay, so that's today's video. We've assessed the baseline steel structure, we've assessed the arbitrarily laid up composite structure, and we've then optimized it. And what we've seen is that the arbitrarily laid up composite structure in this example, actually there's no benefit compared to steel, when looking at stiffness to weight ratio. It's not until we optimize it and taking into account variables, objectives and constraints that we see a real benefit from using composite structures. We're seeing this thing is nearly 3 times greater, or it's about 3 times better in terms of the stiffness to weight ratio. However, it's not manufacturable. And in the next video, then we'll change those variables from real numbers to discrete numbers, re-optimize it, and compare the stiffness to weight ratio. Okay. If you have any questions on any of that, let me know. And like I say, we'll have a look at that in class, and we'll go through that in class together. Okay, thank you. Cheers. Bye-bye.